Hey everyone, and welcome back to The Explainer. Today, we're exploring something pretty incredible, the phenomenon of bending stress. We're drawing directly from the structural engineering notes of Dr. Boudica Weerasinghe. Have you ever looked up at a massive skyscraper or driven across a huge steel bridge and wondered about the invisible physics keeping those structures standing under all that immense weight? Well, today, we're demystifying those exact internal forces. To kick things off, I want to tap into your own physical intuition. Just imagine grabbing a thick paperback book, or maybe a plastic ruler, and bending it with your own hands. You can obviously see it bow into a curve, but what is actually happening deep inside the material itself? Like, what invisible forces are waking up inside those fibers to fight back against your hands and stop the object from snapping in half? All right, here's how we're going to tackle this today. We'll start with the basics of simple bending, and then establish the rules of the game. After that, we'll go inside the bending beam, translate what we see into the math of bending stress, and wrap things up by calculating structural strength. Section 1. The basics of simple bending. So, when a load is placed on a beam, bending moments and shear forces immediately spring into action. The bending moment is literally trying to bend the beam, but, and this is key, the beam doesn't just sit there and take it, it fights back. Internal stresses are immediately created to resist this external bending, and this process only stops when every single cross-section of the beam sets up full resistance. Now for this explainer, we're focusing on a very specific, idealized condition called pure or simple bending. This just means the bending moment is perfectly constant and there is absolutely zero shear force slicing through the material. It's basically the perfect laboratory condition for us to study internal stress. Moving on to Section 2, the rules of the game. To make the incredibly complex physics of bending actually solvable, engineers have to use a mandatory set of assumptions, which Dr. Weersinghe's notes clearly lay out. First up, we assume the material is completely homogeneous and isotropic, which is just a fancy way of saying it's the exact same stuff throughout and behaves identically in all directions. Second, it has to obey Hooke's law, meaning we stay within its elastic limit so it actually bounces back into shape. Third, flat, transverse sections of the beam have to remain perfectly flat even after they bend. Fourth, every layer inside the beam is kind of a lone wolf. It expands or contracts completely independently of the layers directly above or below it. And finally, the material's modulus of elasticity, or E, is exactly the same whether you're pulling it apart or crushing it together. Basically, in an engineer's perfect theoretical world, everything behaves exactly as it's told. Which brings us to Section 3. Inside the bending beam. Now, check out this transformation. On one side, you've got a perfectly straight, unloaded section of our beam. On the other side, under pure bending moments, which you can see represented by those heavy black circular arrows marked M, the beam deforms into a distinct curve. We're literally taking that flat, rectangular cross-section and warping it. And notice how the vertical lines, those transverse sections we just assumed would stay flat, they remain straight, but they are now angled toward a central point high above the beam. So what's actually happening to the horizontal fibers running the length of this beam? Well, it's an intense microscopic battle. Above the middle of the beam, the material is thrown into compression. The fibers up there are literally being shortened. They're getting violently squished together. But below the middle, the exact opposite is happening. Those fibers are thrown into tension. They're elongating, stretching out, and pulling apart as the curve widens at the bottom. So you've got crushing on top and tearing on the bottom, all happening at the exact same time inside a single piece of material. And this brilliantly illustrates one of the coolest aha moments in structural engineering. Think about it. If the top is getting shorter and the bottom is getting longer, common sense tells us there has to be a point right in the middle where it switches over, right? And there absolutely is. Amidst all the chaotic stretching and squishing, there is a zone of perfect peace. We call this the neutral axis, or the neutral layer. It's a specific layer of fibers inside the beam that is neither shortened nor extended. Because its length hasn't changed by a single microscopic fraction, it's not stressed at all. Literally zero stress right in the beating heart of a bending beam. Take a second to look at the horizontal line labeled E1 to F1 here. This is exactly where our unstressed neutral layer lives. If you trace the angles of the bent beam upwards, you'll see they meet at a point called O, which is the center of curvature. The distance from O straight down to our peaceful E1 to F1 line is the radius of curvature, represented by that big R. Every layer above this line, squished. Every layer below it, stretched. But E1 to F1 remains absolutely, perfectly unchanged. Let's translate this into Section 4, the math of bending stress. Don't worry, the math here is just a translation of what we just visualized, and we can walk through this derivation logically step by step. Step 1. Engineers calculate the exact change in a fiber's length. Since the neutral layer is distance r, a layer below it is distance r plus some tiny distance we'll call y. With a little basic geometry, we find the change in length is simply y times the angle of the bend. Step 2. We apply Hooke's law for strain, and strain is really just the change in length divided by the original length. Step 3. Because stress and strain are intimately linked by the material's elasticity, this mathematically proves an incredible rule. The stress on any given fiber inside the beam is directly proportional to its distance from that peaceful neutral layer. And that leads us to this beautifully elegant equation. Stress intensity, which is F, equals the modulus of elasticity, E, divided by the radius of curvature, R, all multiplied by Y, which, again, is the distance from the neutral layer. The logic here is just brilliant. Because E and R are constant for a specific bent beam, the stress F depends entirely on Y. The further a fiber is located from the neutral layer, meaning the higher that Y value gets, the higher the stress intensity it experiences. So, the absolute maximum stress is always felt on the extreme top and extreme bottom skins of the beam. All right, final stop. Section 5, calculating structural strength. Enter the section modulus, represented by the big letter Z. This is the elegant solution engineers use to measure a cross-section's physical resistance to bending. Z is calculated by taking the beam's moment of inertia I, which is basically how its shape is distributed, and dividing it by Y max, which, as we just learned, is the maximum distance from the neutral axis to the extreme outermost fiber. A higher section modulus means a stronger, stiffer beam. Actually, this is exactly why an I-beam is shaped the way it is. It pushes the material as far away from the neutral axis as possible just to maximize Z. So, the crucial point all comes down to this final climax equation. M, the moment of resistance, equals F max multiplied by Z, meaning the maximum bending moment M that a beam can safely withstand before failing is simply the maximum allowable stress of the material times the geometric section modulus. These two factors, the raw strength of the material itself and the physical shape it's molded into, combine forces to completely resist the external bending moments placed on it. This simple formula is literally the gatekeeper of structural integrity. So we've traveled from a bending paperback book all the way to the fundamental equations of structural engineering. The next time you cross a massive suspension bridge or even just step onto a balcony, I want you to look at the steel and concrete underneath you and ask yourself, where is the neutral axis? Because right at that very moment, millions of invisible fibers inside that beam are frantically stretching apart and crushing together, fighting a silent, epic battle just to keep you safe, while right in the center, a perfectly unstressed layer of material rests in total peace. Pretty amazing, right? Thank you so much for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.